Hi and welcome to Gaffy's Grinds. This is video 15 in our series on fuels as part of organic chemistry. And the subject of today's lesson is going to be the alkynes. So before we jump in, we're going to do a quick recap, a quick bit of revision that's necessary just to catch up before we check out the alkynes. So very quickly, here I have a model of a molecule. Okay, I'm going to describe it to you now. The black atoms here are carbons. So I've got two carbon atoms, and each carbon atom has four single bonds around it. So we've got three single bonds with these white atoms, which are hydrogens, and then we've got another single bond to another carbon atom. So each of the two carbon atoms is surrounded by four bonds, and there are six hydrogens attached all together. So the first thing I would like you to do is name that molecule. So by speaking your answer out to the screen now, I want you to name that molecule. Okay, so first of all, how do we process this? Again, this should be second nature to us now. We've done the naming systems for this molecule already. Okay, the first thing to note is that there are two carbons. So when we have a molecule that's got two carbon atoms, we show this using the prefix eth, E-T-H, like that, eth. So eth means two carbons. As the end of the name, then, we will put the family name which it belongs to. This is a molecule where the carbons are all have four single bonds around them. So it's a molecule of carbon and hydrogen where the carbons have four single bonds around them. If they have four single bonds around them, then they belong to the homologous series, the alkanes. Alkanes functional group is that all the molecules have all carbon-carbon single bonds like this. Now, if we have a molecule that's an alkane, then we show this with the suffix at the end of the name ane. So the suffix ane means that it's an alkane. So what are alkanes? Well, alkanes are what we call a homologous series. So what is a homologous series? So I want you to explain that to me by speaking your answer to the screen now. What is a homologous series, please? Okay, so what you should have said is that a homologous series is a group of chemicals. That's the first thing. It's a group of chemicals. What else do we know about it? Okay, so you should have said things like they have similar chemical properties. So all the molecules in the group have similar chemical properties. They have the same general formula, They have the same functional group. They do similar chemical reactions, and we prepare them in similar ways. So if we wanted to make all the members of a homologous series, they would have a similar method of production. Those are the key things about a homologous series. Now, what is the general formula for an alkane then? The general formula. Well, the general formula for an alkane, first of all, actually, before we do that, tell me what the formula for ethane is, please. What is the formula for ethane? Okay, I'm hoping that you said C2H6. So C2H6, that is the molecular formula of this particular substance, ethane. Right, we're going to take a look at this molecule now. Okay, here I have a molecule that has two carbons again, but this time it's only got four hydrogens. So each carbon is connected to two hydrogens, and then the carbons are doubly bonded to each other in the middle. So I've got a double bond between the two carbons. So C double bond C, and there are four hydrogens, as you can see there. What is the name of this molecule, please? So speak in your answer to the screen to answer. Well, again, it's going to be eth, because eth means two carbons, ETH, like this, ETH. Okay, it's not an alkane though. Alkanes have all single bonds around the carbon, and this one does not. This has a double bond. So the functional group of this is that it's got a C double bond C. Functional group is a carbon-carbon double bond. To what homologous series does the carbon-carbon double bond belong to? What is the functional group of what homologous series? Well, functional group of the alkenes is the C double bond C, alkenes. So this is an alkene. So that means we end the name with the suffix ene, alkenes, ene. That's ethene. What is the general formula, please? Like that. Oh, what is not the general formula? What is the formula of this ethene? Okay, the formula for ethene is C2, 2 carbons, H4, like this. Remember, the alkenes are yet another homologous series. So they are a second homologous series. So a different group of chemicals, and all of the alkenes will have this C double bond C in them. They will all have that functional group. They will differ by a CH2 unit. So to make this bigger, I would add on a CH2 to it. And they have a similar method of preparation, similar chemical properties, etc. So that's a definition we've gone over before, and I expect you guys to know it. Right, the next one I want to introduce you to is this next homologous series. It is this molecule. As you can see, I've got 2 carbons again, and this time each carbon is only connected to 1 hydrogen. So there is just 1 hydrogen attached to each carbon. And as you can see, the carbon in the middle is triply bonded to the other carbon. So the 2 carbons have a triple bond between them. Now remember, carbon is always going to make 4 bonds. So we have to account for those, and they are accounted for here. And they have been accounted for in all the molecules. All the molecules have had carbons with 4 bonds. This one has a carbon-carbon triple bond. Okay, I would draw that like this. So C. Oh, sorry, I'm going to do it. Just change the color to black. We've got C triple bond C with 1 hydrogen each side like this. That's how I would draw it. We have a new functional group here that we've not seen before, and that is this here, C triple bond C. This is a new functional group. What is a functional group? Speak your answer to the screen now. Functional group. What is a functional group? Speak your answer to the screen. Okay, a functional group, and this is what you should have said, is an atom or a group of atoms which give a molecule its characteristic properties. So the group of atoms here is the 2 carbons that are triply bonded. So the C triple bond C, as I've shown here, is the functional group of this homologous series. Now, this homologous series belongs to the family Alkynes. It's a 3rd homologous series, the Alkynes. The Alkynes, the first thing we can say about it then is the same as the alkanes and the alkenes. Whatever the name ends in, that will give you the suffix for the name of the compound. So the name of any alkyne always ends in -yne. So it will always be something or something -ine, yne. Okay, I'll show you how that works now. So that's the first thing about an alkyne. Well, what are we going to call this chemical then? Well, this chemical has 2 carbons. Okay, so as usual, if you've got 2 carbons, it starts with eth, ETH. And because it's an alkyne then, it ends in yne. So ethyne is the name of this chemical. And the nice thing is that we only need to know one of these guys. So we only need to know one of the, just this one, just ethyne. It's the only alkyne on the course. Of course, there will be other molecules that have this C triple bond C. And instead of one of these hydrogens, I could add another carbon and add a chain, and this molecule will get bigger. So long as you've got the C triple bond C in there, though, that means it's an alkyne. Now, what about the general formula for this. So the general formula for adding alkyne. Well, let's go back to ethane for a second and start with something we're familiar with. The general formula for an alkane is this. It's CnH2n plus 2. So you can use that formula to work out the formula of any alkane. So that's what we call a general formula. So this here in the box here, this is a general formula for an alkane. So to work it out, for example, ethane, well, N is equal to 2. So N is equal to 2 for eth because eth means 2 carbons. So N is the number of carbons. So if we let N be 2, well, then this is C2 and it's H2 times 2 plus 2. That's going to give me C2H4 plus 2. And that gives me the overall formula, C2H4 plus 2 is 6. So that was how I would work out the formula for an alkane with 2 carbons. So we use the general formula. So this in the box here is called a general formula. And all the alkanes have the same general formula. We have one for the alkenes as well. The general formula for alkenes, it loses that plus 2 off the end, because to make an alkene, you have to take away 2 hydrogens from an alkane. So that gives us the general formula, CnH2n. So however many carbons is, you have twice the amount of hydrogens. So for example, for n equals to 2, then we have C2 and H2 times 2, or C2H4. That is the formula for a 2-carbon alkene. Well, what about the general formula then for an alkyne? Well, the general formula for an alkyne, you may have noted a pattern. The pattern to go from alkane to alkyne, to go from all single bonds in an alkane to make a double bond in an alkene, we had to lose 2 of the hydrogens. That was the difference. We had to take off 2 of the hydrogens to make the double bond. Okay, when we do that, we lose the 2 on the end. So to get the general formula for an alkyne, we're going to lose 2 more hydrogens. And we show that like this, CnH2n minus 2. There are actually 2 less now. So each time we were taking away 2 from the formula. And if we use this to work out the general formula for an alkyne, if we imagine that n is equal to 2, as in the example above, then we would say it would be C2H2 times 2 minus 2. So that's C2H4 minus 2, which is C2H2. So the actual formula for this substance up here is C2H2. That's ethine. Just before, we're going to do some practice in the second couple of questions, but just before we do, I'm just going to give you guys one more to do here. So find me the formula for an alkyne with 4 carbons, please. So 4-carbon alkyne. So pause the video now and do that, please. Okay, so you should only be playing the video if you pause the video and you found the formula for a 4-carbon alkyne. It works like this. Well, a 4-carbon alkyne means N is equal to 4, and that would give me this formula, C4, where N is equal to 4, and you get H2 times 4 minus 2. That would give me C4H8 minus 2, which gives me C4H6. C4H6 is an alkyne with 4 carbons. Well done if you got that right. Right, it's time to do some general practice now. So I've got a couple of questions for you to practice on the alkynes. So I want you to pause the video and I want you to try to do those questions, please. Now, from memory, so from memory, not looking at any notes or not looking at anything you've written down already. So from memory on a blank page, please. Pause the video. Okay. You should only be watching the video now if you've tried the questions. Here come the answers to the questions. I'm going to have to draw some of these out. So it says, from memory, draw the first alkyne. So just again, from memory, we draw the first alkyne. The first alkyne is C, triple bond C, and a hydrogen each side. It's a very important point to make at this stage. Why is this the first alkyne with 2 carbons? Why don't we have an alkyne with 1 carbon? We had alkanes with 1 carbon. Why can't we have alkynes with 1 carbon? Well, remember what the functional group is. The functional group is C triple bonds C. You can't have a C triple bond C if you've only got 1 carbon. If you've only got 1 carbon, it can't be triply bonded to another carbon. So the first alkyne has 2 carbons. You have to have 2 at least to be able to make a triple bond. Okay, so that's the first alkyne. Name this compound. This would be ethyne. Well done if you got that right. Write the general formula for an alkyne. The general formula for alkyne is like this: CnH2n minus 2. Good job if you got that right. And write the molecular formula for this molecule. Well, it's C2H2. C2H2. And you can use the general formula to work that out, although it's pretty simple by just looking at it. You can see this one. But if you had a big long molecule, it might not be that simple. All right, well done on those questions. That's the way we work on this channel. Always we try little bits at a time and then practice, and it makes it really manageable. Okay, right. The next thing I want to point out is the shapes of the carbon atoms, or the shapes of the molecules. So in our lessons before on bonding, when we did study bonding, we would have learned how to name the different shapes that we can find in molecules. If you're not sure what I'm talking about, then you should go back to the chapters on bonding, and you should look for the shapes of molecules. So look in the playlist for bonding and look for the video on shapes of molecules. Now, this is going back to ethane. This is an alkane. Carbon can make 4 single bonds, as it is here. When carbon makes 4 single bonds and is surrounded by 4 atoms. So if I take this carbon here, for example, the one you can see, this carbon is surrounded by 1, 2, 3. It's attached to those 3, and it's attached to the other carbon. I know that might be hard to see, but it's attached to this carbon and these 3 hydrogens. When we've got a central atom, this carbon, surrounded by 4 atoms, this gives us the shape of the tetrahedral, a tetrahedral shape. It's a 3-dimensional shape. And we would draw it like this, a carbon with 4 single bonds around it. Whenever you have carbon attached to 4 atoms with 4 single bonds, we call this a tetrahedral shape. Tetra means 4. Hedral means points. So there are 4 points around the carbon. That's where the name comes from. 4 points. So that's the tetrahedral shape. And all of the alkanes have these atoms here. These carbons, tetrahedral carbons. So anytime you see carbon bonded to 4 other atoms, that means it's got tetrahedral geometry or tetrahedral shape. When you get this type of carbon, you've got carbon with the double bond. Now this carbon is only attached to 3 other atoms. It's only attached to these 2 hydrogens and this 1 other carbon. It still has 4 bonds. It's just one of them is a double, and one of them is a double which points in the same direction. So essentially now you only have 3 points around this carbon. So you've got a carbon with 3 separate points around it, not 4. We don't have 4 different atoms around it anymore. When the carbons are like this, as you can see, this one will lie flat on my palm. So it's all in the one plane. If you think of it, I could put it in between 2 loaves of a sandwich, right? If you think of it, 2 loaves of bread, I could put one on the top, or 1 slices of bread, I could put one on the top and one on the bottom. And this fits like a slice of ham in the middle because it all lies flat in one plane. With the tetrahedral carbons, I can't do that because it's 3D, okay? is three-dimensional, which means I can't get it to lie flat. It's not in one plane. It's not flat like this was. So this is obviously a separate shape of carbon. And we can show this like this. When we've got carbon double bonded to another carbon and we've just got two other atoms around it like that, we can identify these carbons. We usually, if you were asked to do this, you would draw a circle around it like this. We would identify this carbon. Actually, do you know what? I should include the double bond here as well. So I'm going to draw it like that. I would identify this carbon as having a planar geometry. Planar. This is planar because it lies flat. It's a planar geometry. It's not three-dimensional like those carbons in the alkane. If we take a look at the alkene, you will see I can also put this flat in the sandwich. So this essentially is planar, or in fact it's a straight line, so it's linear, but it also sits flat in one plane. So this is a linear shape. And these carbons are not tetrahedral either, clearly, because there's not 4 points around them. In fact, there's only really 2 points around them. This carbon has only one atom attached here and one atom attached here. So that is just a linear geometry. It's two-dimensional. It is not three-dimensional like a tetrahedral. Okay. So that is the geometry. Okay, so it's practice time now. That means more questions to check your understanding. So we're going to go and we're going to have a go at some more questions. Okay, so questions 1 to 4 there is based on the formula and the geometry of the molecule ethyne, or the alkynes in general. So what I would like you to do is I would like you to pause the video and I would like you to do them questions now, please. Okay, and as usual, guys, I keep forgetting to repeat myself, but always trying to do these questions from memory. Okay, so draw the displayed formula for ethyne. So the displayed formula shows you the atoms, position of the atoms and the bonds. So the displayed formula of ethyne, we've got 2 carbons because it's eth. So I'm going to draw 2 carbons here. Here's carbon number 1 and carbon number 2. It's an alkyne, ethyne. That means it's got a triple bond. So carbon, carbon, triple bond. And then it's got 2 hydrogens, one each side like that. So each carbon atom has 4 bonds. So they are satisfied. They have a share of 8 electrons. And each hydrogen has 1 bond and has a share of 2 electrons. So octet rule has been reached for both of those electrons, or all of those atoms there. The next question, draw a ring around any carbon with planar geometry. Well, obviously, this carbon and this carbon both have planar geometries. They both lie flat because they do not have 4. They do not have 4 separate atoms around them, so they are not tetrahedral. They are linear, or they will lie flat in one plane, so planar. Okay, linear or planar. Number 3, in terms of geometry, how are alkynes different from their corresponding alkanes? Excuse me now, I just need to fix a mistake here. 1 second. Okay, so alkynes will contain some planar carbons, they'll definitely have some planar carbons because they have a C triple bond C. So the alkynes have to have these planar carbons. Now there might be tetrahedral carbons attached if you make a big long chain, but it will definitely have some of these. It has to have 1 carbon-carbon triple bond for it to be an alkyne. Whereas the alkanes contain only tetrahedral bonds. It does tetrahedral carbons. It doesn't matter how long you make this chain. If it's an alkane, it will have all tetrahedral carbons. Every carbon will be attached to 4 other atoms. You could make a chain that's 40 of these long, a big long alkane, but all of the carbons will be tetrahedral in an alkane. That's the difference. Whereas an alkyne will always have some of these carbon triple bonded to another carbon, we'll have some planar carbons. Last one, how are alkynes similar to the corresponding alkenes? Similar to the corresponding alkenes. Well, another mistake. Alkynes and alkenes are similar because they both contain some planar carbons. So alkynes, that's C triple bond C, and alkenes, C double bond C, both of them contain that functional group, and that functional group has planar carbons. So both alkenes and alkynes have planar carbons in them. That's how they're similar. Okay, good job. On to the next little bit now. We're going to be looking at a use of alkynes now. Okay, so how scientists or people in general use these. Well, the main use comes from the actual fact that this functional group up here, this C triple bond C, is highly reactive. Highly reactive. Now, when we have a carbon that is not completely surrounded by hydrogens, so like this one here, a C triple bond C, this is not completely surrounded by hydrogens. I could break these bonds and add on more hydrogens. What word do I use to describe this molecule then if I could add on more hydrogens? So on 3, speak your answer to the screen. 1, 2, 3. Okay, I refer to this molecule as unsaturated. It's unsaturated, okay, because of the triple bond. Alkenes are also unsaturated because of the double bond. You can break these bonds and add more hydrogens. Alkanes are not unsaturated. These are the opposite. These are saturated. They already have 4 bonds on the carbon. The carbon cannot make any new bonds, so you cannot add in any extra hydrogens. So these are saturated. These ones are not. You can break the double and triple bond and put more hydrogens. This is what makes them highly reactive. The triple bond space here is an area that has a lot of electrons in here. Because it's a triple bond, there are 3 pairs of electrons in here. So 3, that's 6 electrons altogether. That's a very negative area, 6 electrons being shared between these 2 carbon atoms. And that makes them very reactive because electrons will attract other things, other atoms that are positive, for example. So that makes them very reactive. So the C triple bond C is highly reactive. Now, with that in mind, it gives us a use. A use that we have for ethyne. So if we, I'm just going to rub out some of this stuff here for a second. We have the formula for ethyne, which is C2H2. Sorry, that should be a 2. Ethyne. Now, the use that we have for ethyne is that it's used in welding. Now, in welding, we take a piece of metal and we take a second piece of metal. And the aim for the welder is to get these 2 pieces of metal to stick together. So that's piece of metal 1, and this is another piece of metal. And we do this by trying to get them to join together. And this happens by taking a piece of metal on a rod. So we have this rod, and on this rod is a piece of metal. Okay, just going to try and make it look a little bit better. That's a piece of metal, and this is what we call a welding rod. Okay, a welding rod. Now, the welding rod has metal on the end here. This is more metal. And what we want to do with it is we want to get that metal to melt so that we can pour it into the gap between these 2 pieces of metal. And then when it hardens, it will stick the 2 pieces of metal together. That's the basic idea behind welding. So we take our welding rod, which is basically a handle and a piece of metal, and we want to melt the metal that's on the end. Now, obviously metals have a high melting point, which means that they need a lot of heat. They need very high temperatures to get them to melt. So if we take ethine and we mix it with oxygen, because oxygen is required for any combustion reaction, remember? So we're going to have to add oxygen to get it to combust. We're going to take ethine and get it, mix it with oxygen and burn it. We're going to get a very, very, very hot flame. And the very, very, very hot flame of the combination of ethine burning and oxygen is able to melt the metal on the welding rod. This metal then is directed by a very skilled operator called a welder, and it's basically transferred into the gap between two pieces of metal. And the idea here is you need to get it very deep into the joint of the two metals, and then we want to get them to stick together. So once the hot metal then solidifies again, it should be strong enough to hold the two pieces of metal together. So that's the idea. Ethine is mixed with oxygen to create a flame that's hot enough to melt the metal of a welding rod and then to stick two pieces of metal together. So this is one of the uses of ethine. And the reason why that's possible is because it's such a reactive substance. It burns at a very high temperature. So the use here is it's used in welding because it burns at a very high temperature when you mix it with oxygen. So this here is a use of the alkyne ethine. Okay, the old name for this, and it's still actually some people still use it today, is what we call oxy, because we're mixing with oxygen. And the old naming system for alkynes gave this ethine the name acetylene. So this is often still referred to as oxyacetylene welding. But we're not going to worry too much about that name because it's a very old, outdated naming system. There's a much better naming system, much more up-to-date one now. And this particular chemical is now called ethine, but acetylene was its old name. Okay, so what I'm going to get you to do is everything that we have drawn here and written here, you can take down as notes because that's the notes on ethine, on alkynes. Okay, so I'm going to get you to pause the video and take that down now as notes, please. Okay, so that's the only, that you should only be watching the video if you have taken that stuff down and you're happy, you've got nice tidy notes. You can do them better in your copy than I'm able to do on the screen. I'm doing my best, but it's not the easiest. Okay, the last thing we're going to have a look at is the properties. We're going to consider the properties of alkynes. And one of the main properties, a couple of the main properties we're going to look at is their solubilities. Okay, solubility. We're going to look at solubilities and we're going to look at melting and boiling points. So the first thing to consider if we want to know about the properties of a substance, particularly if we want to know the temperature that they melt and they boil at, well, we need to take a look. I don't know what's happening there. We need to have a look at the molecule again. If we consider the molecule ethine, and we want to know, does the molecule have polar bonds? That is a really important, critical question in helping us to understand the properties of a substance, is to understand the bonding that's going on inside the substance. When we discussed or when we learned about bonding before, we would have learned previously that if we have a substance that's, say, a liquid, that means that we have particles which are close together like this. So this is the molecules. These circles represent the molecules, and they are close together. And if we want to convert them into a gas, that means we have to allow them to spread out more. And they do this by having more energy. So these lines here show these particles having more energy. So they're now particles that are gaseous. They have turned into a gas. And these energy lines or movement lines show that they are moving around quickly. Okay. So obviously we have to add energy to get them to go from a liquid to a gas. And we do this by heating. So how much we have to heat them, well, that depends on the forces of attraction between the particles when they are a liquid. So different substances have different forces of attraction that hold the molecules together. And we need to know how strong are those forces of attraction. Well, to answer that, we need to know if they've got polar bonds. And to know if they've got polar bonds, we need to check a couple of things out. Now, I'm going to assume that you guys know how to work out if something has a polar bonds in it, or if it has non-polar bonds in it. If you're not sure how to do that, then again, you really need to go and check out the videos on bonding before you continue with these videos. Okay. First of all, it's important to account that this is going to be the same case for any of these hydrocarbons, any of the alkanes, alkenes, and alkynes. All of these are molecules that have hydrogen and carbon only. So if they're only made of hydrogen and carbon, what is a word we can use to describe them? Only hydrogen and carbon. So on 3, speak your answer to the screen. 1, 2, 3. Okay, you should have said that these are hydrocarbons. So first of all, if we consider this area in here between the two carbons, there are electrons being shared in the bond between the hydrogens and the carbons. There are 6 electrons in here. Now, to find out if the bond is polar or not, we would have to consider the electronegativities of the 2 atoms in the bond. Well, both the atoms are carbon, so they are the exact same electronegativity. That means that this bond is non-polar because neither of these atoms attracts the electrons towards themselves. So you don't get any dipoles created. Again, if you do not know what these words mean, then you need to go back and watch the videos on bonding. The carbon-hydrogen bond, these are not the same atom. So there's a possibility that that could be a polar bond. We need to check the electronegativities. Well, the electronegativity of carbon is 2.5 and the electronegativity of hydrogen is 2.1 or 2.2, sorry. So carbon is 2.5 and hydrogen is 2.2. So if we do 2.5, take away 2.2, that gives me 0.3 as the difference in electronegativity. That is not enough to make it polar. So that falls below our range of 0 to 0.4, we consider to be non-polar bonds. So no dipoles are created. We do not have delta positive and delta negative areas, partial positive and partial negative areas. So no permanent dipoles are created in these molecules because it's the same no matter which molecule you're talking about. We're still talking about bonds of carbon to hydrogen or carbon to carbon. That's all you find in these molecules. There's no other atoms in here. So because they are non-polar bonds, that means that all of these molecules will only be attached to, if I now draw a second alkene, or alkyne, sorry. So if I draw a second molecule of ethine, the question is, well, these are attracted to each other in some way, these 2 molecules. This is what causes them to have a boiling point or a melting point is the forces holding the two molecules or attracting them together. So what strength or what type of forces are these? Well, the answer is they're very weak. They're very weak attractive forces because there is no permanent dipole. No permanent dipole. A dipole is just an area of positive or negative charge. And remember that delta positive attracts delta negative, and we don't have any delta positive and delta negative here. So we don't have any dipoles. All we have is electrons moving around inside the molecules, creating temporary dipoles. So we do create temporary dipoles. Again, guys, this will make much more sense if you have watched the bonding videos first. So we do create temporary dipoles just from the movement of electrons inside the molecules. Basically, you've got moving negative charges. Electrons are negative charges. They're orbiting around the atoms here. So these electrons are constantly orbiting around the molecule. They're moving around. And as they move, the negative charge is constantly moving. And the area that it's not presently in are very slightly positive for a fraction of a second. Now, these electrons are moving really, really, really quickly, which means wherever they are is very slightly negative for a fraction of a second, and an area where they're not is very slightly positive for a fraction of a second. But it only exists for a tiny fraction of a second because the electron has already moved somewhere else in a second later. So these are what we call temporary dipoles, and they create these tiny little attractions for other molecules. So this molecule here is very weakly attracted to a second molecule of the same type. So weak strength. This is what we call a van der Waals force. Van der Waals forces are basically forces of attraction resulting from temporary dipoles from electrons moving around inside a molecule. They are very weak, and they mean that any substance that has these types of forces is going to have low melting and low boiling points, because it really doesn't take much energy to separate these types of molecules and allow them to turn into vapors and to overcome the forces of attraction. So that's the first point to make, is that alkenes, and alkynes, they're all hydrocarbons, only hydrogen and carbon. They all have non-polar bonds, which means they all have only temporary dipoles. Therefore, they will have only van der Waals forces, and if they have only van der Waals forces, they will have low melting and boiling points. So in general, they have low melting and boiling points. Well, what about the different lengths of hydrocarbons? We learned this when we were studying back of fractional distillation. We said some of the alkanes and alkenes have higher melting points and boiling points than others. Why is that then if they only have van der Waals forces? Well, of course, the van der Waals forces are created by orbiting electrons, moving electric charges. The more electrons you have moving around, for example, if I show some electrons whizzing around in black, creating temporary dipoles, and I show some moving around in red, creating temporary dipoles, and I show more in green, creating temporary dipoles. Again, the more electrons you have, the more temporary dipoles you're going to create, and the stronger the van der Waals forces are going to be. So molecules with more electrons, or more atoms having more electrons, are going to have bigger van der Waals forces than others. So for example, this here, this is C2H2. If I was to compare that to something like C25H 48, which would be an alkene or an alkyne with 25 carbons, this is going to have a higher BP, and this is going to have a lower BP, BP standing for boiling point. And the reason for this is this has more electrons because it's got way more atoms. And if it's got more electrons, that means it's going to have more temporary dipoles and stronger van der Waals forces. So therefore, higher boiling point. That's the first property that we looked at, is melting and boiling point. What about a second? We're going to have a look at a second property. And that is the idea that if I take a beaker of water, so this is water, and I'm going to bubble in some ethine gas. So I've got a tube here, and I've got a supply of ethine gas. When we go on to make ethine gas, or if you've already watched the experiment where we made it, we actually put the tube into something called a beehive shelf, and on top of it, we were able to collect the ethine gas in a test tube of water. So we had the water in a test tube, it was upside down, and the ethine bubbled up through the gas or through the liquid, and it collected at the top, and it pushed the water down, push the water out of the test tube. This is called collecting a gas over water. And it's a very useful way of collecting a gas. Now, this proves to us that that ethine is not soluble. It does not dissolve in water. Ethine is not soluble in water. None of the hydrocarbons are soluble in water. The reason for that is if we take water, we take a beaker of water, and I'm going to show again in blue, and we zoom in and we take a look at the particles. Here are water particles, which I'm showing loosely, fairly close together, loosely attached. These are held together by forces of attraction called, no, I'm not going to draw them as solid lines because that might confuse you. These are what hold these are the types of intermolecular forces holding the molecules of water together. These types of forces are called hydrogen bonds. So water molecules is held together by what we call hydrogen bonding. Now, for something to be able to dissolve in water, water molecules have to be able to hydrogen bond to them. So if I was to stick ethine in here as a different color, so if I was to stick bubble ethine atoms in here, or ethine molecules in here, shown in green, if we want them to dissolve, that means that the water molecules have to give up their hydrogen bond with each other and hydrogen bond to the ethine. So some of these hydrogen bonds have to break, and instead they have to form hydrogen bonds with the ethine molecules. Now, if that is able to happen, then you will get ethine dissolving. So if you are able to successfully hydrogen bond water molecules to ethyne like this, then you would get them to dissolve. So water will only break the hydrogen bonds from each other if you put something else in there that they can hydrogen bond with. And because ethyne cannot form hydrogen bonds, and the reason for this is they only have van der Waals forces between them. Remember when we discussed up here, it's van der Waals forces that hold ethyne together, not hydrogen bonds. Because they cannot form hydrogen bonds, ethyne does not dissolve in water. So what does ethyne dissolve in if it does not dissolve in water? Well, it can't make hydrogen bonds, so it won't dissolve in any material that it would have to make hydrogen bonds with. What it will dissolve in is materials that it can just make van der Waals forces with. If it can interact with them through van der Waals forces, then it will dissolve in it. So other organic products that don't have water in them, so things like cyclohexane, for example, cyclohexane. Cyclohexane is another molecule that does not make hydrogen bonds. It just has van der Waals forces between the particles. And when something just has van der Waals forces between the particles, then something like ethyne can dissolve in it. Okay, so it's time to do some more practice questions now. So here they are. So just start off by doing questions 1, 2, 3, and 4, please. And then I'll stop and help you do number 5. So just do 1 to 4, please. Pause the video. Okay, so here are the answers. Okay, so explain in terms of reactivity, how are alkynes similar to their corresponding alkenes? Well, alkynes are more reactive than alkenes, or than alkanes, sorry, that should be alkanes, that should say, sorry. Alkenes are more reactive, alkynes are more reactive than alkanes because they contain a C triple bond C, which is highly reactive. So the C triple bond C is highly reactive, which makes them more reactive than the alkanes or the alkenes, actually. Okay, so the alkynes with the triple bond are the most reactive. Double bond is the next reactive, and single bonds are not very reactive at all. Last one, or second one, sorry. What type of intermolecular forces are found between molecules of ethyne? That would be van der Waals. So van der Waals forces exist between molecules of ethyne. Question 3, explain why alkynes have low boiling points. Alkynes have low boiling points because van der Waals forces do not require much energy to overcome them. They are very weak forces and they can be easily overcome by a small amount of energy. So even at lower temperatures, these can be boiled. That's the idea there. Number 4, why is ethyne useful as a welding gas? Why is ethyne useful as a welding gas? Ethyne is useful as a welding gas because when it's mixed with oxygen, it burns at a very high temperature. The last one you have to, so question 5 we're going to take a look at now. Complete the sentences. So you have to, I have given you the sentence starters, and you have to make a sentence that is logical. Okay, you have to make a sentence that is logical. Now you don't have to, you might not have the exact same thing as me, but it has to be a sentence that makes sense. So if I just get you started on this now, I will show you how to do with the first one. Okay, so ethyne dissolves in cyclohexane because, so we would write this out, ethyne dissolves in cyclohexane because, well, cyclohexane does not form hydrogen bonds. Okay, it only forms van der Waals forces. So, and this is because the molecule is non-polar. It doesn't have dipoles. Okay, because, so we could say because neither molecule or neither substance would say. Neither substance has dipoles. So when we actually look at the type of bonding inside both of these atoms, neither of them will have dipoles, neither of them have positive and negative areas. So the idea here is that like dissolves like. If you have things with dipoles, then they will dissolve other things that have dipoles. If you have things that don't have dipoles, then they will dissolve in other things that don't have dipoles. Right, so you go ahead now and do number 2 and number 3. See if you can make a sentence that makes sense. So pause the video and do those now. Okay, so you should only be watching the video if you've tried to do the last two there. So ethyne dissolves in cyclohexane, but you could have there, it does not dissolve in water. That would be a good second sentence, something like that. The last one, ethyne dissolves in cyclohexane, therefore, well, we could say ethyne dissolves in cyclohexane, therefore these two liquids are miscible. That means that you can mix them together. That's probably a decent place to finish up the video. So we have learned about ethyne or the alkynes and their properties and what they're used for. Okay, so that is the alkynes, and I'll see you in the next video.